Welcome back. In this video, we're going to introduce the node voltage method, and we're going to find out exactly how we can apply the node voltage method to analyze different circuits. Now, the node voltage method is actually one of my favorite techniques in circuit analysis. The reason is because this method is very methodical. Once you follow these particular steps and you understand exactly how to use Ohm's law, the job is basically done. Now, like I mentioned, there are some steps you need to follow. The first step I suggest you follow is to identify all the essential nodes. So I know this is an essential node. I know this is an essential node. And we know we're going to have one more essential node at the bottom here, right? So I'm just going to take this point right here to be that essential node. And we can call it node 3 if you want to, right? Now the thing is, when using the node voltage method, you have to choose one of these essential nodes as your reference node, aka your ground node. Usually, that's going to be the essential node that has the most interconnections. So when we look at this, we know that the essential node for this particular circuit, we're going to choose as the bottom node. So this node right here is actually going to be our reference node. So let's say you have a voltmeter, right? And you know a voltmeter has a black and a red terminal. So when you was to put the voltmeter on this particular circuit diagram, the red part is going to go where the node is, which is going to be right here, and the black part is going to be where the reference node is, and that's going to tell you the voltage at this particular node. So that's why you have to choose a reference node when using node voltage analysis, okay? Now we know we had 3 essential nodes in total. Now when we're starting to write our node voltage method equations, we're always going to have one less than our total amount of essential nodes. So we started off with 3, but when we chose a reference node, we only have 2 essential nodes remaining, which means we're going to have 2 node voltage equations that we have to write. Now before we continue, I want to just state something here. We're going to be using the node voltage method. The node voltage. You know, anytime we think of node, what do we think about? We usually think of KCL, right? Because we know KCL deals with the current in a node. And we know, according to Kircchoffs Current Law, the algebraic sum of currents in a node must equal 0. So when we talk about node, we are usually referring to the current in that particular node. And that doesn't change. It does not change. I know it sounds weird because I say node voltage, but then we talk about the current. It's like, wait, what is going on, right? That's how I felt. Now, the thing is, I need you to break this down, right? Try to understand what I'm about to say. Replay this if you need to. We're going to be using the node voltage technique. The node voltage technique. Which means we want to find the voltage at that particular node. We want to find the voltage at that particular node. You understand? So we're going to be using the node voltage technique because we are interested in the voltage at these 2 nodes, okay? So we can label these nodes. I'm just going to label it as 1 and 2. Now because we're finding the node voltage, I think it's only fitting to also put a V with them because we want to find the node voltage. So I'm going to label it V1, V2. Okay? Now that we have labeled our essential nodes where we're interested in finding the node voltage at those particular nodes, the next thing I want us to understand is when we are solving these particular circuits using the node voltage method, one of the most important things to remember is no matter what you know about that circuit, you're always going to assume that the current is going to be leaving that node. Remember a few videos back, we talked about Kircchoffs Current Law. We know some current was entering the node, some current was leaving the node. But in this particular technique, in the node voltage technique, if you are using the node voltage technique, you must always assume that the current is going to be leaving that node. It doesn't have to be so, but that's what you have to assume to get these problems correct. So let's start to work some problems, and then we'll continue from there. So let's start to solve this problem. How many equations are we going to need? Well, we're going to need two equations, one for V1 and one for V2, right? So I'm just going to write this as NV, stands for node voltage at V1. Okay, so when we start to write this equation, I want us to assume that the current is going to be leaving this node. And remember, if you do not know the current in that particular branch, you're always going to write the current as a relationship using Ohm's law, which is going to be voltage over resistance. So remember, current equals voltage over resistance. Okay, so let's look at this. We're going to start with this branch here. Now when we look at this, right, this one is kind of easy to see. We have a current source that's actually going to be in this branch here. So this 12 milliamp of current is going to flow in this direction, and it's going to go through this 10K resistor, and it's going to enter this node here. But because we always assume that the current is going to leave the node, we're just going to write this 12 milliamp of current as a negative current. So instead of it being 12 milliamps, we're actually going to write it as negative 12. And because we have milliamps, we're just going to write it as times 10 to the negative 3, because we know milli is going to be 10 to the negative 3. I'm going to put it in brackets, plus we have the current that's going to be flowing in this branch here. Well, think about it. We know we're going to have a current, and we don't want to introduce any new variables, right? So we're going to write it. So we're going to write it as a relationship using Ohm's law. That's going to be the voltage at this node is V1, right? So we have V1 over 5K, which is 5,000. So this right here is going to be the current flowing through this resistor. So ignore this for now, right? Just ignore this. This doesn't really matter to us, right? I know it's there, I know it's V1, but just ignore it, right? We actually care about the voltage at that particular node, not what this voltage is labeled as. Now we have a current in this direction here, so we're going to assume that the current is going to flow away from the node, so we're going to write it as plus the voltage at node 1 minus the voltage at node 2 divided by the resistance, which is 5,000. And all of that equals 0. Now let's start to simplify this. So we can multiply the entire top by 5,000 to get rid of this 5,000. So we can have negative 12 times 10 to the minus 3 multiplied by 5,000 plus V1. We know if we multiply 5,000 by this particular term, those two 5,000s are going to cancel out. So I'm not even going to write it back. I'll write it back, right? Let me just write it back. 5,000 over 5,000 plus V1 minus V2, 5,000 equals 0. I mean, it's also going to be over 5,000, right? Now, this 5,000 and this 5,000 are going to cancel out. And this 5,000 and this 5,000 is also going to cancel out. So when you simplify this now, this is going to give you negative 60 plus V1 plus V1 minus V2 equals 0. So we're just going to simplify this equation. We're going to carry this negative 60 over to the next side. So we're going to get 2 V1 minus V2 equals 60. So this is our first equation, right? This isn't the answer, but this might be able to help us later on. So this is our first node voltage equation that we written at node 1. Now let's do for node 2. I'm actually going to do it right on the side here. Let me just draw a little line. We're going to have node voltage at node 2, right? So we want to find the current that's going to be leaving this particular node, which means that we're just going to assume that the current is going to leave this node and go in this direction, and that direction. You could be wrong, but we're just going to make that assumption, right? So the current leaving the node going in this direction now is going to be V2, which is the voltage at node 2, minus the voltage at node 1, divided by the resistance, which is 5,000. So that's going to give you the current flowing this way. Then we have plus, we have V2, which is the voltage at node 2, over 4,000, which is going to be the resistance in this resistor here. So we have V2 over 4,000. That's how we find the current in this particular resistor. And finally, we're going to have plus. We know that these two resistors are in parallel, which means they're going to have the same voltage. So if this is V2, we know this is also V2, right? Because these two resistors are parallel. So we're going to have V2 over 4,000 equals 0. Now when we simplify this now, we're going to have 4,000 V2 minus V1 plus 5,000 V2 and because we have V2 two times and they had the same denominator, we're actually just going to write this as 2V2, right? So we're going to write this as 2V2 equals 0. Of course, you don't have to skip that step, but for the sake of space, I just skipped that step, right? Okay, now I'm going to simplify this. We're going to have 4,000 V2 minus 4,000 V1 plus 10,000 V2 equals 0. So when we simplify this some more, we're going to get negative 4,000 V1 plus 14,000 V2 equals 0. So this right here is going to be our second equation. So we have our first equation and our second equation. Okay, now we're going to use matrices to solve for the unknowns V1 and V2. Of course, you can do substitution if you want to, but I'm just going to do matrices. So we have 2, negative 1, and we have negative 4,000 and 14,000. We have V1, V2, and that's going to equal 60 and 0. So remember, we want to find the inverse of matrix A and multiply it by matrix B. So we want to calculate the inverse of matrix A and multiply it by matrix B. So when I put this in my calculator now, that's going to give us 35 and 10. Therefore, we know V1 equals 35 volts and V2 equals 10 volts. Now, what does the question want us to find? So we know the voltage at each one of these nodes. We know V1 is 35 volts and the voltage at node 2 is going to be 10 volts. Now the question wants us to find V1 that's labeled in the circuit, right? So that's going to be the voltage at this 5K resistor. Well, when we look at this circuit, the voltage V1 is going to be the same voltage at this node right here. Therefore, we know the value of V1 because we found the voltage at this particular node, and we know that voltage is going to be 35 volts. So we know the value of V1 in this particular circuit, and that's going to be 35 volts. So our answer is going to be V1 equals 35 volts. So this is our first problem using the node voltage method. It's not hard, but these are the key steps you must remember when solving problems that involves the node voltage method.